Okay, in 84 we're doing the same kind of stoichiometry, but we have to take it one step further because it's now asking for volume. So before we can do anything, we need the balanced equation. You might be wondering, how was I ever going to come up with that? But if you look at your chart in your book, okay, in the chart you see that there's actually an equation that involves, see right here, there's O2, H plus, and H2O. So all they really did was they took the H2 equation from the chart that had H2O and the O2 equation from the chart that had H2O, and they just combined them. So when you combine these two equations, you're going to end up finding that the overall equation is H2 making 2H2 making H2 plus O2. Sorry, 2H2O making 2H2 plus O2 is the overall equation. And here the flow of electrons is 4 electrons. So we're going to need that to solve this problem. It says that they apply a current of 2.5 amps. And we know we can rewrite amps as 2.5 coulombs per second. And it's applied for 15 minutes. So then the next thing we need to do is 15 times 60 to get seconds. Okay, and that's going to give us the number of coulombs that is applied. So once we have the coulombs applied, we can then use Faraday's constant to go from 96500 coulombs in 1 mole of electrons. And once we have moles of electrons, we can use, there's 4 moles of electrons for every 2 moles of H2. Okay, and that's going to give you 1.17 times 10 to the negative second moles of H2 being produced. And if we have that much moles of H2, we can then use a mole ratio to find the O2, but we also wanted to find the liters, so now you have this, you can just do 1 mole as 22.4 liters at STP. Okay, so that's going to give you, it looks like 0.262 liters of H2, and then we'll use that, and we're going to have, we should have half as much O2, so 0.131 liters O2.